Hundreds of smaller containers fit snugly inside hundreds of boxes, which sit inside the large cargo container. And the wonder material that holds most of the small containers together is corrugated fiberboard. With paper made from farmed southern pine trees and up to 70% recycled fiber, this Georgia-Pacific factory in Richmond, Indiana, produces 65,000 tons of corrugated fiber a year. You probably call these cardboard boxes, but the industry begs to differ.
If you look at most boxes or most containers, they used to be made out of layers and layers of fine paper that makes a board, and they used to call that cardboard. And a lot of packaging was made out of the cardboard back then. Now there's a lot more product out there that's made more out of the corrugate or out of the corrugated sheets that we make.
In 1890, a Brooklyn printer and paper bag maker named Robert Gare invented the corrugated carton, and ultimately changed the way we pack and ship today. Today's corrugated boxes are stronger and use less paper than cardboard boxes.
The boxes we make here are made of 3 different components. You have right here, which is what we call the liner part of the board. It's a brown, typically looks like a craft paper bag out of a grocery store. The inside of the box is what we call a medium, which we flute.
It's a very similar process to someone who might be ironing the wrinkles out of a shirt, but we're ironing wrinkles into our sheet. We are taking heat to condition the paper and steam to make it receptive to forming the flute shape, and then starch to be the glue or the bond to take the 2 separate pieces of paper and glue them together. So similar to 2 sets of gears coming together, the medium will go down in between them and be formed into the flute.
Architects have known for thousands of years that an arch with a proper curve is the strongest way to span a given space. The same principle applies to corrugated fiberboard. Arches in the corrugated medium, when anchored to the liner board, resist bending and pressure from all directions. When a piece of combined board is placed on its end, the arches form rigid columns, capable of supporting a great deal of weight. When pressure is applied to the side of the board, the space between the flutes acts as a cushion to protect the container's contents. After the medium is fluted in the almost 300-foot-long corrugator, the final layer is glued to the fiberboard.
So then at that point, you have 2 of the 3 substrates joined together, and they will then travel to the other end of the machine where we will apply a cold glue, which is a polyvinyl acetate, very similar to an Elmer's glue, and we will put another thin adhesion of glue on the flute tip and then bond the printed liner on top of that.
This machine takes the sheets that we just saw laminated. We feed them through this line 1 sheet at a time. They're delivered to a cutting station where I'm literally cutting them like a cookie cutter. I've got cutting roll, I've got creasing roll inside the die that can actually cut out the board and crease it where it's supposed to be creased. It goes on to station 2 where we literally strip out the scraps.
Scraps are recycled into new boxes immediately.
Once it's stripped, it's delivered to a pallet, and they're taken flat off to the next station.
The finished box is folded and glued into various shapes to fit and protect everything from juice to toys.
We can take a blank like this. With the fold and gluer, we can turn it into a carton like this. We can also take a blank in this form. We can turn it into something that'll pack flat in the case for the customer, so that at their end, they can just pop it and fill it.
America's corrugated container board is so highly prized that more than 660,000 tons of it are exported to factories throughout the world in standardized shipping containers. Both the containers and the boxes can hold a lot of goods, but what if you've got to store America's petroleum reserve or its food surplus? You'll need the biggest containers in the world. In 2004, the value of containerized cargo entering United States ports totaled more than $750 billion. Containers were returned on Modern Marvels, here on the History Channel. We now return to containers on Modern Marvels. When When it comes to containers, none rival the size of the U.S. Strategic Petroleum Reserve. Located along the coast of the Gulf of Mexico, the SPR has a capacity of 727 million barrels of oil.
The Strategic Petroleum Reserve actually has 4 different facilities where we store crude oil, 2 in Louisiana and 2 in Texas.
The crude oil contained in the SPR is housed in natural underground geologic formations, salt domes.
A lot of people don't realize the size of salt domes in the Gulf Coast area. This particular dome is called Bryan Mound. The Bryan Mound Dome is located approximately 2,000 feet from the surface of the Earth, and at the 2,000-foot contour, it is approximately 1.5 miles wide.
Within Bryan Mound and other SPR salt domes are massive cylindrical caverns where the crude oil is stored. The entire SPR contains 62 of these mammoth caverns.
We currently have 20 caverns here at Bryan Mound with a total capacity of 254 million barrels subsurface.
If you can imagine the size of the Astrodome, if we were to fill up the Astrodome with crude oil, it would be equivalent to the amount that we can fill up one of our caverns.
In 1975, President Gerald Ford signed the Energy Policy and Conservation Act, which created the SPR. This was a direct response to the economic crisis generated by the OPEC oil embargo of 1973-74. The country needed a safety net for future political, economic, and natural disasters that might threaten the supply of one of America's most vital resources. The daunting question: where to contain hundreds of millions of barrels of oil?
The thoughts that were brought up were above-ground storage, underground storage. They realized that the Gulf Coast was the most feasible location to store crude oil underground in salt domes. The majority of the refining process is located in the Gulf Coast. The pipelines are located in the Gulf Coast. And there were actually some salt domes that already had some leached caverns, solution mine caverns.
Unlike traditional salt mining, which uses machines to dig for the salt, solution mining injects millions of gallons of water into salt domes to create caverns.
It's a process in which we use raw water to dissolution the salt, much like you would dissolve table salt at your house. And we use approximately 7 barrels of raw water to create 1 barrel of cavern space.
The way that these underground containers are performed or created is the introduction or the drilling of 2 holes approximately 4,000 feet into the salt dome itself. Now those holes then have extended casings in it, a pipe within a pipe, and we introduce water into those pipes, the inner pipe, and begin to dissolve the salt. The dissolved salt becomes brine, and the brine comes out the annulus or the outer pipe.
As the brine is extricated, crude oil takes its place and is stored until needed. The oil benefits from the natural high-temperature subsurface.
The geotechnical heating of the crude oil keeps it a consistent composition because we have homogeneity across the crude oil.
In order to extract the oil from its underground reservoir, the SPR performs a drawdown.
We pump raw water in through the brine stream to the bottom of the cavern. It displaces the crude oil, which is on top of the brine, and that comes out through our crude oil header.
Oil is lighter than water, so the 2 substances naturally separate. The oil is then segregated, metered, and distributed to various terminals and refineries.